Hey guys, how's it going? In the second semester, we're going to be doing a lot of work with integrals, which remember is area under the curves, right? So we're going to have to become comfortable with evaluating these integrals. And there's different rules that we need to know and become comfortable with, and they're on page 285 of our textbook. There's a table 5.3 where they have all those different rules. I think that the best way to get comfortable with those, though, is just by doing problems. Okay, so the problem I'm going to do right now is problem number 2 from page 290. And this problem will give us really good practice with those properties I'm talking about. Okay, so in this problem, they give us the value of 3 integrals. Okay, so let's remember what an integral is. Remember, the integral is area under the curve, right? So what this statement is saying is that if there's a function f of x, the area in between that curve, that function, and the x-axis, going from an x value of 1 to an x value of 9, is negative 1. All right, so what that means is there's going to be more area under the x-axis between the curve than above. So maybe it looks something like this, where this area is 1 unit bigger than this area. Okay. Although that's a little bit contradictory to what this statement is saying, because this statement is saying from 7 to 9, if here's 7 and here's 9, that area under the curve is 5 units. All right, so maybe instead it looks something like that, where this area is actually going to be more than this area. Pardon the bad drawing. But let's remember that's what it says. From x equals 7 to x equals 9, the area under the curve is positive 5 units. So that means it's got to be above. So this is probably a better drawing, although not to scale, than this one is. So I'm going to erase that one. And since this one's so bad, I'm going to erase that one too. This statement is talking about some totally other function, h of x, and the area under that curve from x equals 7 to x equals 9 is 4. Okay, so now let's do some work. Let's do these problems. All right, so let's look at this one right here. Notice this statement is almost the exact same as this statement, right? The only difference is that negative 2. But that shouldn't upset us, because one of the properties says when we multiply by a constant, in this case negative 2, we can just pull it out front. Okay, so this is a completely equivalent statement. All right, and this part in the box is identical to one of our givens, so we can just replace it. So we have a negative 2 out front times negative 1, giving us a final answer of 2. Okay, so remember, anytime we multiply by a constant, we can just pull that out front. All right, the second problem, the bit of information they're using is that when we have addition, we can just take the integral of this part and add it to the integral of this part. Okay, so we can split this one up to look like this. Okay, so anytime there's addition, we can split it up into 2 separate integrals. Be careful, you can't do that with multiplication. Okay, if we have a function times a function, you cannot just split them up. All right, but in this case we can, because it's addition, or subtraction is okay when we get to that part. But here we know that this part, the integral from 7 to 9 f of x dx, is 5. And the integral from 7 to 9 of h of x is 4, giving us a final answer of 9. All right, looking good. Let's look at this third part. Okay, so here we have some subtraction, so we can split it up. And then we got some multiplication by constants, so we can pull those out front. So this integral we can rewrite like this. Okay, so the subtraction, let us split it up, and then constants we could pull out front. All right, so excluding the 2, this part is 5, so 2 times 5 is 10. And then the integral part here is 4, 3 times 4 is 12, 10 minus 12 is negative 2. All right, let's move on to the fourth one. All right, here are the limits. It's almost exactly this statement, right, except for the limits. Here we go from 9 to 1. Here we go from 1 to 9. Seems like a problem, but it's not. One of the properties says if you want to flip the limits, you can. You just put a negative out front. So this is completely equivalent to this. Okay, and this part we know is negative 1, so we have a negative sign out front. So the opposite of negative 1 is positive 1. Looking good. All right, this one's a little bit trickier because it goes from 1 to 7, and we don't have anything from 1 to 7. But we do have 1 to 9, and we do have 7 to 9, but we don't have 1 to 7. Okay, so what we have to do is this little bit of information. Use this. The integral from 1 to 7, f of x dx, plus the integral from 7 to 9, f of x dx, equals the integral from 1 to 9 of f of x dx. And as you get more comfortable with integrals, this will seem kind of obvious. It may not at this point, but the area under the curve from 1 to 7 plus the area under the curve from 7 to 9 has to equal the total area from 1 to 9. Okay, but we can talk more about that in class when I can make a drawing and point to things and such. Okay, so here we want to evaluate from 1 to 7. We don't know that, but we do know 7 to 9, 5, and we do know 1 to 9, -1. This is the one we don't know. So just to make my notation easier, I'm just going to call that x. So I'm going to subtract 5, so x equals -6. All right, last one. So let's see, the last one. With subtraction, I'm going to split it up. So 9 to 7, h of x dx, minus 9 to 7, f of x dx. And I'm going to erase this just to make some room. Okay, but once again, we got to do the flipping of the limits thing, so that's no big deal. So 9 to 7, that's going to be the opposite of the integral from 7 to 9, and that's h of x. So it's going to be -4 minus 9 to 7. So I got to take the opposite of the 7 to 9 one, so minus -5. So 4 minus -5, that's, I'm sorry, -4 minus -5, so that's -4 plus 5, giving us a grand total of 1. Okay, so there's an example problem for you. If you have any questions, please write them down and bring them to class. See ya.